Okay, so for number 5B on the worksheet, we do need the answer for 5A. So the molar heat capacity of iron is going to be 29 joules per mole Kelvin. We get that just by converting grams to mole from the specific heat capacity. Part B asks if we have 1,239 joules of heat added to 5.6 moles of iron at 12.2 degrees Celsius, what is the final temperature of the sample? So there's kind of two ways you could go about this. You could convert moles to grams and then use the specific heat capacity that's given. Or since we have the molar heat capacity, we can just keep that in moles and then just solve for the final temperature. So we're going to go ahead and do it that way. So remember, we have Q equals the molar masses times the molar heat capacity times delta T. So the heat added is 1,239 joules equals our moles of 5.6 times the molar heat capacity, 29, times our change in temperature. Remember, that's going to be final, so TF minus initial, which is 12.2 degrees Celsius. I could go ahead and convert this to Kelvin now or later. Either way, it doesn't really matter since it is addition and subtraction for difference, so I went ahead and just did it at the very end. So if we solve for TF here, the final temperature, what you end up getting is 19.83 degrees Celsius. If we add 273 to that, we get basically like 292.8. So we can just round that up to 293 degrees Kelvin. Okay, so I added the 273 at the very end. You could add it to the 12.2 right here, and you should get that same answer for the final temperature. Okay. Next, we're going over the second number 6, so the 6 without all the parts to it. So you can go ahead and fish that out as I find my stuff. Okay, so number 6, how much heat is released when 24.8 grams of methane is burned in excess oxygen gas to produce carbon dioxide in water? And we're given this equation, CH4 plus 2O2 yields CO2 plus 2H2O, and our enthalpy of the reaction is equal to negative 802.3 kilojoules per mole. So this enthalpy of reaction relates directly with this equation here. So if we have 1 mole of methane, 2 moles of oxygen, then this is the heat that would be released, or the enthalpy change that would occur during the reaction. But we didn't necessarily react 1 mole. We reacted 24.8 grams of methane. So the first thing we have to do is figure out, well, how many moles is that? Because our chemical equation is in terms of moles. So we're going to take 24.8 grams and divide by the molar mass. So 1 mole over molar mass of methane, which is 16.04 grams. And you get about 1.5 moles. So this heat enthalpy change for the reaction, negative 802.3 kilojoules, is in terms of 1 mole of methane. So that's per 1 mole of CH4 that's reacted. But we reacted 1.5 moles. So we are going to multiply this, which cancels out the moles, and that gives us negative 1,240 kilojoules of heat that were released in this reaction when we react 1.5 moles of methane. Now, if the coefficient in our equation was 2, I would have a 2 over here because it would be per 2 moles of CH4 that's reacted. But since it's 1, that's why the only thing I have to do is multiply. I don't have to divide by anything. So if we were given it in terms of O2, we'd be dividing by 2 and multiplying by the moles of O2. Okay? So that's it for this 6.4, 6.6 worksheet, but there were also some questions on the guided reading notes in section 5.5. We're going to go over those. So the first question was section 5.5, number 12, where we have aluminum and its specific heat capacity of 0.91 joules per gram Celsius. This aluminum had a mass of 100 grams, was sitting in boiling water at 100 degrees Celsius. It's removed from the boiling water and quickly added to water in a styrofoam coffee cup, which is acting as a calorimeter. The water in the coffee cup has a mass of 100 grams and was at an initial temperature of 22.0 degrees Celsius. Calculate the final temperature of the water-aluminum mixture. Assume that no thermal energy is lost to the surroundings. So this one, there's kind of two unknowns here. We don't know the amount of heat that was lost or gained by the water or aluminum, and we don't know the final temperature. It's asking about the final temperature. But if we look, we have the Q of the water, the heat that the water essentially gains, and that's going to be equal to the mass of the water, 100 grams, times the specific heat capacity, 4.184 joules per gram Kelvin or Celsius, times the change in temperature, which is going to be X, what we're solving for, minus the starting temperature of the water, which was 22 Celsius. So that's the Q of the water. Then we have the Q that the aluminum is releasing. So that would be equal to the mass of the aluminum, again 100, times the specific heat of aluminum, 0.91, times the change in temperature, in this case it's going to be X, minus 100. So the original temperature of the aluminum before it was added to the water is 100 degrees Celsius. So if the heat lost by the water is equal to, numerically, the heat gained by the water, then we can basically say that this relationship exists. The Q of the aluminum is equal to the negative Q, or the opposite Q, of the water. So what I'm going to end up doing is setting these two equations equal to one another with the one change that I'm going to basically reverse the sign in everything in here. Okay? So I'm going to do negative 100 times 4.184 times, and then I'm going to do 22 minus x, which is really negative x plus 22. Just kind of rewrote it to look nice. And then equals everything on this side of the equation. 100 times 0.91 times x minus 100. Okay? So from here, if I distribute, I get negative 418.4, and then multiply that by x, plus 9,204.8. And then I can set that equal to 91x minus 9,100. Okay, so I just distributed everything in there, basically. Now I can solve for x, and I get 509.4x equals 18,304.8. Divide for x, and I get 35.9 degrees Celsius. So that's going to be my final temperature for both of those solutions. So basically you set the Q's equal to each other, set these equations equal to each other, but you have to remember to flip the sign of one of them because one of them is losing heat, one of them is gaining heat. So they're going to be opposite in sign, essentially. The second question on this was for number 15, which has a few parts to it. So 15a is asking what's the value of the change in temperature, which is pretty straightforward. They tell you that the temperature increased from 25 to 50.4. So if you find the difference, you should get 25.4 degrees Celsius, which is just 50.4 minus 25. Okay. Part B gets a little bit confusing. So it says calculate how much heat was transferred from the combustion reaction to the bomb calorimeter. The information they give you is that the heat capacity of the bomb calorimeter is 8.25 kilojoules per degree Celsius. So in your textbook, if you look, there's a picture of a bomb calorimeter. It's basically like a big vessel. But notice that the heat capacity is not in joules per gram degree Celsius, because it's not a measurable substance like it was like for water, where we said, oh, we're adding 100 grams of water. So there's no grams involved. So instead of our usual Q equals mc delta T, we're just going to be dealing with Q equals C, specific heat capacity of the calorimeter, times delta T. Because if you notice, in the specific heat capacity, there is no grams to account for there. So all that we have to do for this is take the heat capacity of the bomb calorimeter, which is 8.25 kilojoules per degree Celsius, and multiply by our delta T, which is 25.4 Celsius. Celsius is going to cancel, and we end up with 210 kilojoules. Now, was this amount of heat released or gained? It's asking how much heat was transferred from combustion reaction to the bomb calorimeter. So for the bomb calorimeter, it should be gained, but you could also say that 210 kilojoules were released from the methane combustion that occurred in the bomb calorimeter. So if you want to say that way, you would say negative 210 kilojoules, but that is how much heat was transferred to the calorimeter. So the sign, positive or negative, depends on which way you look at it. That was the amount. 210 was the amount of heat released to the calorimeter. Part C says calculate the number of moles of benzene used in this experiment. Sorry, I think I said methane. It's benzene. It says that we have 5 grams of benzene. So this is a simple molar mass conversion. Benzene is C6H6. So if you go to the periodic table to add up those molar masses, you would get 1 mole over 78 grams approximately. Grams would cancel out. 5 times 1 divided by 78, you get 0.064 moles. Then part D says calculate the delta H for the combustion reaction in units of kilojoules per mole. Include the sign of delta H in your answer. So in terms of the reaction, again, this positive or negative 210, in terms of the reaction, the benzene that combusted, it released energy. So the change in Q is definitely going to be negative in terms of the reaction. So we have negative 210 kilojoules. And then remember that the enthalpy change of the reaction is in kilojoules per mole. So we're going to divide by the number of moles that we reacted of benzene, which is 0.064 moles. If you plug that into your calculator, you would get negative 3,280 kilojoules per mole. That is our answer for 5.5, number 15. All right. Let me know if you have any other questions over the weekend. I did put a post on there from update from College Board that just happened today, so look at that. I'm sure you'll be pretty happy. Yeah, let me know if you have any questions.